Welcome back to the JRM-01 project. A big goal is reached. We installed all the covers, all the servos and lots of electronics inside the fuselage. We call it JRM Mini because it is much smaller than our final version. This one is equipped with two 50mm EDFs as main engines, also a 50mm front fan and two 76mm wing lift fans. But it has all the main features like the vector nozzles, the droop noses, and also the deflection surfaces that are movable later on. And even the main design will be the same on our final project. But at first we have to evaluate if our construction will work. And this is much easier on a 60% scale jet than on this 2-meter long version. Okay, let's start with the vector nozzles. Here we are designing them. At first we have to make clear that the rods can go through the fuselage and the servos got their right position. And this you can see there, the rudder vector servo is attached on the upper side and the two elevator or AL vector servos are attached on the lower fuselage right below the ducting itself. And this is how it looks like designing a push rod. This will be printed later on. This is a test. That's why the bottom is flat for better adhesive on the print plate. It will be printed from carbon fiber reinforced PLA. And the first tests are really good. I cut M2 thread on each end, you can see there. And the only problem was that you need a smooth transition from this 2mm size shaft to the wider one, otherwise it will break. They will be used as push rods also in the jet when they finally reached the test phase. Okay, let's go on with designing on the jets. Here we can see the lower fuselage and the servo covers. And every cover we put onto the fuselage has to designed into the whole surface that it is best possible aerodynamic and also for the flow of forces. All the time we got an eye on a nice looking design which is functional and also aerodynamic, and especially that we got our needed stiffness. We make a section view that we can see if the material thickness is enough for the use we needed. And especially there on the rear of the jet with the vector nozzles, there is a lot of technique installed, so we need much room inside. And it has also be rigid because these skids underneath should save the vector nozzles itself when you land with high angle of attack or you got some obstacles on your ground where you land. So there are different ways that have to be solved at the same moment. So every step you do, you must think a lot of forward steps at the same moment, that maybe you don't remove too much material that you would weaken the fuselage too much in this area. Also that it stays aerodynamic and looks nice. And this is the most difficulty we got to do. And so Mark and I, we got different parts at the workflow. While Mark is doing the CAD, I'm thinking how to design it. And this works very well because the workload at this, what we are doing here, what you see, is absolutely enormous. And you have all the time to be super concentrated, because when you make one mistake now, this mistake could be very time consuming to remove it afterwards. And we try to go from the most important parts like the main wing joiners or the ducting step by step to the not so important parts like let's say the skids or the vector nozzles. and this works out quite nice, so that the most important things are already installed. Why you see this? Especially the carbon tubes into the fuselage, which give a lot of stability and stiffness. For instance, if we would first install these vector servos and afterwards we try to install carbon tubes and we see, oh, there is a servo right in the way, this could be a big problem. And so there is a clear system we follow while constructing and designing these super complex jet. And after every servo is installed, there is the next point that is absolutely necessary, and these are small channels for the cables and the wiring, because every servo needs electric power, and they also can't run through the main joiner or through the ducting. We have to find separate ways and separate areas for them, and here you can see the cable channel from the wing into the fuselage, and right from this we let's say drill a channel to the aft underneath of the vertical stabilizer, and this is for the rudder servo and for the elevator servo. And we also want to keep the wiring easy, that we don't have let's say everywhere for every servo its own cable channel. We want to combine most servos in one channel to keep a clear electronic and also find the shortest way to keep everything lightweight. And you see everywhere is something in the way. This is the 6mm hole for the main joiner, and we go underneath with our cable channel. Luckily the root of the wing is quite thick, so there is enough space for it. And this section view, this helps a lot, or X-ray view, let's say, helps a lot to identify if we cut into something external. And we also have to keep an eye on that we print with lightweight PLA, which you can't print super thin, so we try to keep the walls at about 3mm minimum thickness. And the second thing is we can't put support into these cable channels without the possibility to remove it. So there again a lot of things we have to keep an eye on before we can say this is the final solution. Yeah, for the support this is a special problem, and so we divided the whole jet into segments. This is caused by the printer size. We optimized this here for the Bambu Lab printer. This has a size of 256mm in cubic, and the fuselage parts fit very nice to it. And this is one thing that helps to keep the support there where it is reachable and is removable, so that at the end the wiring can put through it. Also these wire channels has to be big enough that the connector doesn't stuck in the corners. And not everything we can't check here on the computer. A lot of things we will first see when the parts are printed and we are dealing with them in reality. For easy installation of the wires, we put a lot of radiuses on sharp edges. This will also reduce the need for support, and I think this looks much nicer. And now it's time to install the elevator servos. We need this CLS-0511H. This is a fast micro servo, which is well approved also in the SUXR. It has metal gear and is very strong. And this will be placed underneath, shortly in front of the elevator in this blue area. You can see it there. We got a small library with all the parts we are using on this project, like ball heads, fork heads, joiners, the servo levers. This helps a lot to check if the size of the part will later on fit into the fuselage, and also for the part list we know exactly how many of these ball heads we will need, and yeah, this makes the whole construction for us complete. And also when we want to have a manual for building up this project, it makes absolutely sense to construct or design all these components right in front before you start with your project itself. And here we are installing the hole for the servo, or the servo placement area. And you see this is quite thin, the aft of the fuselage, because it's aerodynamically optimized. But anyway, the servo fits, and there is still enough material to keep it in position and to stay strong. The vertical stabilizer on the upper also helps to keep this area stiff. So we have always to think over if we don't weaken some area too much. This is super important while placing servos or motors or whatever. This means when we make these cutouts, this is removing of material, and we can't weaken any area too much. And when this area is placed, it's time for the cable channel. This one will run from the servo area to the main cable channel, and this has also been made that no support is needed for this area, that it is later on easy to finish the part for all the assembly. So the angle is about 60 degrees on Cruiser sets, so when we make these channels, they can't go steeper than 60 degrees. Next is the bearing of the elevator. This is realized with a 1.5 millimeter carbon rod, and one part is just extra on the outside. This will be printed from PLA. The other bearing is already printed on the fuselage itself. And here we can see again the fully assembled aft of the jet with the vertical stabilizer and also the servos underneath. And now it's time to go to the wing. Here we see again the section view, and now we want to install a motor. So we also take a data sheet of a motor we think that could fit, and redesign the engine for our library, for our part library. This goes quite fast, and it doesn't need all the details. Important for us is almost the size. Here especially the high, because it's quite tight in this little 60% JRM-01 Mini. So the engine has to fit perfectly without running too much outside the wing on the lower side, and it also shouldn't stuck on the covers on the upper side. Here we tested a lot of motors, so even before they will go to the test stand, they have to fit by its side anyway into the wing. And here it is, already with the propeller installed. This time we got an 8-blade one. Also the security nut, it's on its top, and you see this motor is a bit too long. It touches the upper covers. So one possibility would be that we cut the shaft, which we are doing here just for simulation. And while Mark is installing this motor, I was looking for another one. This is not so easy, because there are hundreds of different motors and they are almost the same size, and we need a motor that fits also to the propeller, and especially now to the size in the high, but it has also has to be powerful enough that we can use it anyway. So there are again a lot of needs in every single detail that has to be solved, yeah, and this makes the whole thing, the whole construction of a VTOL jet always difficult, yeah, that you can't make any compromise, yeah. On a propeller plane, maybe there's no problem when you make the motor a bit longer, then you make the nose longer, but our motor is into the wing, and the wing ends on the lower side, and we don't want to have a motor that looks straight out of it, and also the shaft can't get out of the top. Yeah, so yeah, this is just a small detail. And here we are installing the upper axis, the bearing for the two covers. And the idea was that we make it a bit bigger, like a 3mm carbon tube, which is more stiff than the originally planned 1.5mm carbon rod, but it will weaken the levers too much that we go back to the original planned 1.5mm carbon rod. And I printed also the part and check the stability itself, and it is stable enough and rigid enough, so this was okay. But this was also a small detail where we can't say, okay, we want to do this. If you think you solve one problem, you create yeah, 2 or 3 new ones. So on every detail, yeah, you have to be patient and make your priorities, that the sense of the construct is given. And the most important thing for a cover is that the cover is possible to open and close it, and gives us a good upper surface of the wing, because on the upper surface the lift is created, and this is the priority 1, and all other things go below. And that's how we solve every problem step by step. And after this we go to installing the servos, and you see this is quite tight. This will be very interesting how we can install two. In one of the last videos I explained our design with two 180-degree servos, which will be installed in front of the covers. This works super safe, and the servos are strong enough to move these covers under all circumstances, even if you fly really fast, and also if the propeller is running under full throttle. And here we grab the servo out of our part library, installed it on a bottom plate. This is later printed also on lightweight PLA, and this will stiffen the installation area from the servo, because normally there is just one wall or two upper layers from lightweight PLA, and they are quite not stiff enough, especially when we install the servo with some screws. Here we got these two brackets for the size. I think these are not the correct ones, so we have to, yeah, now we got the correct size, and also the ball head is installed. And now we put everything together. There is already one cutout in front of the lift fan where the servo will be placed, and the other one on the other side. And now we have to think how we can solve this in our CAD program, because this is not an easy task to install two servos at the same time. The reason is we want to always simulate the travel of the arms, and that's why the servos are mirrored and got the same distance, are installed on the same level, so we don't have to do this 2 times again. And thanks to Mark, he is super specialized on this, that we can do this in real time. So even if it is a bit speeded up here, this is a very difficult task on a CAD program to do this. And but caused by my testings right in front of this, we know where to place it, and we have an idea how the lever and the drive will come out. So we do not have the design and the placement and the CAD work at the same moment. The design is almost clear where it comes through. Now we just have to put our ideas into the computer and say them, put the servo in there, the right correction, the right position, the right distance from the inlet ring, but you will see in the next moments it is super tight. It is super tight. The area from the outer servo cuts into the outer shell under the droop nose. So we have to move a bit these areas forward to let it fit anyway. But we decided to realize this JRM-01 Mini also as a VTOL to make a complete test of these difficult details. So it makes sense anyway. Also would be super interesting if it is possible to realize. I think this is one of the world's smallest VTOL-Jets, even it is the world's smallest ever built, with 50 millimeter EDF size. So this would be absolutely great goal if we could achieve it. And even not, we want to give it a try. We want to give it a try. And afterwards, all details we are designing now will be upsized to the 70 millimeter size of the JRM-01 and finally to the 90 millimeter size. There we won't get these problems with the space. There we will get much other problems, especially with the stability, because this jet now will weigh about, let's say, under 2 kilograms. This is needed, under 2 kilograms for the mini JRM-01. The 70 millimeter, the medium-sized one, will stay at about 3.5 to 4 kilograms, so the weight is doubled. And on the 90 millimeter size, we want to stay under 7 kilograms. So this is more than 3 times the weight of this small jet. And there are lots of other loads. Even this jet is powered with about 4,000 watts of engine, just the main engines, while the main engines here has together about 1,600 watts. So here on this project, on this actual project, size is the main problem, that we can put all the techniques inside, but we can make big cutouts without the danger that something will break apart. And even if there is a little problem, we just can put a carbon rod in this area and the issue is solved. But on the bigger jets, we will be more focused on the integrity and the stability. But we can just size up the techniques in here, and this make every next size, every next bigger size of the JRM-01 much easier to design, because most of the technical difficulties are already solved. You can see here, this is the front 6 millimeter wing joiner, and we cut with the servo cutout direct in it, but we don't have any chance. If we go more forward, we are completely out of the wing. So we decide that we get rid of this front joiner, because for the small size the rear joiner is enough. This has to be tested afterwards anyway, for sure. But you see, these are hard decisions. There is not put the joiner a little bit more front or more back. There is just no place. If we want to go more back, it cuts into the propeller. If we go more forward, there is just no length where it could go into the wing anyway. Because a joiner has just needs its momentum or its area where it goes through a part. So on the JRM-01 Mini, it is about 11 centimeter for the main joiner. But when you got just 3 centimeter, it make no sense to install this joiner anyway. It will just break off. Yeah. So, but without a joiner, there was finally enough area for the servos, and now the next step is to make the cutouts where these 2 servo arms with the ball heads can run through. At the end, we want to hide the mechanics as good as possible, that you just see that the ducting or the duct covers open up, but the techniques should be hidden. And also for the aerodynamic from the air that is sucked in by this lift fan, it is good when you have closed surfaces, especially on the inlet lip, but a small area we had to cut out anyway in there. But the wall to the propeller itself, itself is still there, and it's also thick enough that it gives the needed stability to the whole construction. And now we do the cutouts and the bottom, because the servo is running 180 degrees from vertical upper to vertical to the lower position. This is the next thing. Yeah, lot of you guys ask why we don't install just one servo for these 2 hedges. And I also had a conversation of a good friend of mine, and he sent me a video where he showed me how to do this solution with just one servo. But for this, there is much more technique above the servo, so it would be too high, and the servo would run under the lower wing, and so we can't use this solution in this small wing. Maybe on the bigger wings we will give it a try to do the movement of the covers with just one servo. But in this actual project here, there is just no other way than to do it with these 2 servos, even caused by the needed area or build height that we got, because this wing is just as big as maybe 2 hands. Yeah, it's a quite small wing, and you see everywhere is coming out an edge of the servo, so we have to enlarge this radius built around the ducting. Also there on the droop nose, on the inner droop nose surface, you can see there is a triangle cut out. Yeah, so we are moving the servos a little bit forward, a little bit back, but everywhere we go, we come out of the part. But at the end, and this is super nice while working on this, Mark and me, we always find a solution where we are happy with. Without getting angry with our project, at the end there is always a solution, and this makes us super happy and gives us super motivation for this project. Sometimes it takes some time to find a good solution, yeah, because you just can't, for instance, size up the whole wing. This is not possible. We got an all-over design, and we have to fit on this design. Yeah, this is there is not at the first moment a solution that you can say, I got it, we just have to do this. No, like I said some minutes before, these first moment solutions create just 3 problems afterwards. So we take our time and discuss every change on the outer design, and also discuss the mishaps that could happen before we do any changes. Afterwards, we just would test out new solution by new solution, but at the end we wouldn't come any step forward. Yeah, and we always check with this section view if we cut into something important. So this is quite one of our working flows. Yeah, to when we decided us to change anything on the outer design, we do this section view to make sure that we don't create any new problem or issue. And when everything looks nice with the new solution, we integrate it and give it the final shape. Yeah, because this is an aeroplane, as you know, and it just don't have to work every detail we put in there. It has to be aerodynamically optimized. Yeah. Even if the lower side is not that important like the upper side on the wing, we are focused to make everything as let's say as perfect as possible. Yeah, with the time we have. Yeah, this is this is now running in I think 5 times faster than in reality. So everything needs a lot of time, and we don't have the time to test out any possible solution. Yeah, so we both, Mark and me, we have to stay clear that our decision is mostly final. And I can tell you the installation of these door cover servos was one of the most difficult parts till now on the whole project. But we learn from this. Yeah, even it is getting very difficult, this will help for a lot of other issues we will have in this project anyway. Because even if we got one final printable design, when it comes to reality and it will be tested, this is a whole new level. And we just need for ourselves a way to handle these problems. Yeah, and that's why we are not, let's say, sad or unhappy about this when it gets difficult. This brings us forward. Yeah, so this is super important. And this JRM Mini is very difficult. I think much more difficult than a bigger size, but it prepares us. It prepares us for the, let's say, easier upcoming sizes, and we know what to do. Yeah, and here we thought over what we do with this edge that is coming out of the surface, and finally we designed to move the whole this whole round surface forward. This means that we make the droop nose smaller. Yeah, luckily it was super big right before. Yeah, this is also something we are preparing ourselves for upcoming problems to make the super important design parts a little bit bigger than needed later on. So there's always a safety margin we have, and we often need this. Yeah, this is but on the other hand, you can't make everything let's say 2 times of the size you needed. Yeah, then your plane will get much too heavy, and an airplane, and especially an VTOL plane, has to be super functional and also super lightweight. Yeah, because we are dealing with, let's say, a little bit inefficient propulsion system. Yeah, this lift fan is the one with the best efficiency at all. Yeah, of course it's a big size propeller. But the other engines, the main engine and the front engine, are EDFs, and they are normally designed for fast flying and not for hovering, like with about 0 airspeed. Yeah, and for on this super low airspeed, they are super inefficient, and that's why we have to have an eye on absolute lightweight construction. Yeah, and that's why we can't do everything bigger in the first stage. Every part on this jet has its needed size. Yeah, and but at the end, you see here, we solved it. There is just a bit of the cover surface missing, where it looks like a hole in the wing. Last step was installing these small levers. They will be printed from PLA later on. Yeah, and after these hard tasks, there is time for fun. Yeah, this is one of Mark's, let's say, mostly loved parts to create some scale features or scale details. But this also is a reinforcement for the inner surface, because I wanted printed, if possible, just with one wall. And if you got just one flat wall, it is not that rigid or stiff as if there are these imprints inside. And it also looks much more interesting with these details. So it's a super nice work sharing between Mark and me. I got an eye on the functionality and that everything works, and Mark makes it as most as possible nice looking. Yeah, and finally we finished the wing covers. Everything is working and fits, and we are super happy with this. It was a really hard task with this wing, but it looks so amazing, and we couldn't believe it in the first stage that we can install in such a small wing a lift fan anyway, but we did it. If there are any questions left, you can write it down there in the comments. If there are any technical things you like to know more in detail. And if you like to support this channel, you will find some links underneath in the video description. And that's it for this video. I wish you a wonderful day, and we will see us in the next episode. Bye bye.